One popular discrete random variable is the binomial random variable. There are basic characteristics of all binomial experiments.
The four properties of a binomial experiment are provided on this slide. First, a binomial experiment consists of n identical trials or a sample size of n. Second, each trial must result in exactly two outcomes. One we will call a success, and the other we will call a failure. Third, the probability of a success is denoted P, and it must be constant from trial to trial. Therefore, the probability of a failure is equal to 1 minus P. Fourth, the trials must be independent. With a binomial experiment, we are always interested in determining the number of successes that occur in n trials, or a sample size of n. Whenever you are given a problem and you suspect that the problem is a binomial experiment, you should go through each of these four steps in order to confirm that it is a binomial experiment and identify all of the parameters. Here we have two examples. We can go through these examples and try to determine if our problem is a binomial experiment. Example 3. We flip a coin 10 times. What's the probability that we get tails exactly 3 times? Example 4. Suppose 70% of applicants for an MBA program are women. If we review 20 applications, what's the probability that exactly 12 applications are from women? Let's first review example 3 and go through each of our four steps to determine if this is a binomial experiment. We flip a coin 10 times and we want to know the probability that we get tails exactly 3 times. Our problem is asking us the probability that something occurs x times out of a larger number of n times that the experiment is conducted. Walking through our four steps. First, our experiment does consist of n identical trials. We flip a coin 10 times, so n is equal to 10. Step 2. Each trial results in exactly two outcomes. Here, when we flip a coin, we either get tails or we get heads. We should always name a success in terms of the probability question being asked, regardless of our personal feelings towards the experiment. Since the probability question above is asking about tails, we should name tails our success in this problem. Therefore, getting a heads would be considered a failure.
In step 3, our p-value is the probability of a success. For this example, that's the probability of flipping a tail on any individual trial. This value is equal to 0.5, since there is a 50% chance of getting a tails on any individual flip. In step 4, for our problem, the outcome of flipping a coin on one trial does not influence the outcome of flipping a coin on another trial. Therefore, we declare that our trials are independent. After stepping through all four of these steps, we find that our problem is indeed a binomial experiment.
Example 4. Suppose 70% of applicants for an MBA program are women. If we review 20 applications, what's the probability that exactly 12 applications are from women? Our problem is asking the probability that 12 out of 20 applicants are women. Let's go through our binomial properties in order to see if this is a binomial experiment. First, does our experiment consist of n identical trials or a sample size of n? Yes, our problem consists of a sample size of n equals 20 applications. Second, each trial results in exactly 2 outcomes. For our example, we do have exactly 2 outcomes for each application. Either it's a female applicant or a male applicant. In this example, since our probability question is asking us about female applicants, we should name a female applicant a success, which makes a male applicant in this example a failure. Regardless of our personal opinions for this problem, since the probability question asked about a female applicant, it was much easier, as you will see in following slides, to name a success a female applicant. In step 3, the probability of a success is denoted P, and it should be consistent from trial to trial. Here, the probability of a success is equal to the probability of getting a female applicant. In this problem, we were told that 70% of applicants are female. Therefore, P is equal to 0.7. Step 4. Our trials are independent. For our problem, the gender of one randomly selected application does not influence the gender of the applicant for another randomly selected application. After checking all 4 properties, we see that our problem is a binomial experiment. For a binomial probability distribution, we define X as the total number of successes and n trials of a binomial experiment. We also define the probability of having X successes and n trials as the combinations formula n choose X times p to the x power times 1 minus p to the n minus x power. N choose X is a combinations formula. This formula tells us if you have n items, the number of subgroups of size X that can be formed. For most calculators, you can Google your calculator model and ask for the combinations formula. The instructions on the site should give you how to accurately compute the combinations formula. You should practice entering the combination problems in your calculator to ensure that you have the correct sequence of keys to yield the proper results. For this first example, you should practice if you have 10 items and you want subgroups of size 6. This formula should give you the number of subgroups of size 6 that can be formed from 10 items. Entering this in your calculator, you should obtain 210. Again, you should practice with another example. If you have 20 items and you want subgroups of size 15, You should enter the combination formula into your calculator to determine the number of subgroups of size 15 that can be obtained from 20 items. Your calculator should give you 15,504. You should also try this with the last example on this slide. Once you become comfortable with how to compute the n choose x portion of this probability formula, you should begin applying this formula to examples. Let's revisit example 3 when we flipped a coin 10 times and wanted to determine the probability that we get tails exactly 3 times. Recall for our problem, we have n equals 10 identical trials. We also have 2 possible outcomes from each trial. We either get heads or tails. Because our probability question asked about getting tails, we named tails a success. The probability of a success, or getting tails, is our p-value, which equals 0.5. We previously discussed that the outcome of one flip does not affect the outcome of another.
For this example, we are trying to find the probability of having x equals 3 successes or the probability of getting a tails on x equals 3 trials. In order to do this, we must use our binomial formula and plug in our parameters. On the previous slides, we found that n equals 10, p equals 0.5, and x equals 3 for this problem. Therefore, we should insert these values into our binomial formula. If we do this, we should obtain n equals 10, choose x equals 3, times p, which is 0.5, to the x power, which is 3, times 1 minus p, or 1 minus 0.5, to the n, which is 10, minus x equals third power. Before entering this into our calculators, we should simplify this expression. In simplifying the expression, we obtain 10 choose 3 times 0.5 to the third power times 1 minus 0.5, which is 0.5, to the seventh power, which is 10 minus 3. If we enter this into our calculator, we should obtain 0.1172. So the probability that we get tails exactly 3 times out of 10 flips equals 0.1172.
Now let's apply this formula to another example. Recall our MBA example, where traditionally 70% of the applicants to the program are women. For this example, we reviewed 20 applications and want to compute the probability that 12 applications are from women. On previous slides, we went through our 4 properties for binomial distribution in order to determine our parameters. For step 1, we determined that we have a sample size of n equals 20 items. For step 2, we identified that there are only 2 possible outcomes for each application. Either the applicant is male or female. In step 3, recall we named a female applicant a success since the question is asking about female applicants, and p is equal to 0.7. And in step 4, we previously discussed that the gender of one applicant does not affect the randomly selected gender of another applicant. So for our problem, we have n equals 20 and p equals 0.7. we take our same basic probability formula and insert our n and p values into the formula. Here we are trying to compute the probability of having x equals 12 successes. So in our formula we have n, which is 20, choose x, which is 12, times p, which is 0.7, to the x power, which is 12, times 1 minus p, which is 0.7, to the n equals 20 minus x equals 12 power. Before entering this into our calculator again, we should simplify this formula. If you try to enter the original formula into your calculator, it is much easier for errors to occur due to parentheses. So we simplify this expression to n choose x times 0.7 to the 12th power times 0.3 to the 8th power. So here, instead of writing 1 minus 0.7, we put the value 0.3. And instead of recording 20 minus 12, we put the exponent 8. If we enter this into our calculator, we should get the value 0.1144. So the probability that we get 12 female applicants out of 20 applications received equals 0.1147.
Now let's get some hands-on practice. Evans is concerned about a low retention rate for employees. On the basis of past experience, management has seen a turnover of 10% of the hourly employees annually. Thus, for any hourly employee chosen at random, management estimates a probability of 0.1 that the person will not be with the company next year. If we were to randomly select 3 hourly employees, what is the probability that one of them will leave the company this year? You should pause the video at this time and then use our 4 steps to identify this problem as a binomial experiment. In going through these 4 steps, you should be able to identify the appropriate n, p, and x values for this example. You should then plug these values into our binomial formula in order to compute this probability.
First, you should have went through the 4 characteristics of a binomial experiment. Number 1, we have a sample size of n equals 3 employees. Number 2, there are only 2 possible outcomes for each employee. Either they will stay or leave. Since the question is asking about leaving the company, we will name a success as leaving the company. In step 3, the probability of a success or an employee leaving the company is our p-value, which equals 0.1. And in step 4, if we randomly select one employee, whether they leave the company or not is not affected by another random employee's decision to leave the company. For our problem, p equals 0.1 and n equals 3, we are looking to find the probability of having x equals 1 success out of our 3 trials. We put our parameters into the formula. N choose x times p to the x power times 1 minus p to the n minus x power. Remember to simplify this expression before entering it into your calculator. When you enter it in your calculator, you should obtain 0.243. So there is a 0.243 probability that exactly 1 out of the 3 employees will leave the company. Most textbooks and our discrete probability chapter online folder provides binomial charts to assist us with computing the probability of events for binomial random variables. In practice, you should always go to the probability tables to see if your N and P combination is listed. If it is listed, you should use the table to obtain your probability values. If your N and P combination is not listed in the tables, you must use the formula on the previous slide to compute the probability of having X successes and N trials, or a sample size of N. If we return to our previous example, our N value was 3 and our P value was 0.1. We should go to the binomial tables to find N equals 3 and P equals 0.1 on the charts. On the charts, we are looking for N equals 3 and P equals 0.1. Here we have N equals 3 and P equals 0.1. So our values right here in this section give us the different probabilities of having X equals 0, 1, and 2, and 3 successes. According to this table, there is a 0.243 probability of having X equals 1 success. This answer matches our answer when we computed this manually. Now, let's continue to use the tables in order to compute events for binomial experiments. For example 3, when we flip the coin 10 times, let's compute the probability that we get tails on less than 3 trials. This probability, the probability that X is less than 3, is equal to and contains the sample points of having X equals 0 successes, X equals 1 success, and X equals 2 successes. Therefore, in order to compute the probability that X is less than 3, we have to sum the probability of having X equals 0, 1, and 2 successes. If we go to the binomial tables, where N is equal to 10 and P is equal to 0.5, we can find the probability of having X equals 0 success, which is 0.001, the probability of having X equals 1 success, which is 0.00098, and the probability of having X equals 2 successes, which is equal to 0.0439. Therefore, the probability of having X is less than 3 successes is equal to the sum of all of the probabilities of the sample points contained in this event. This sum is equal to 0.0538. So there is a 5.38% chance that we will get tails on less than 3 out of 10 trials. Let's revisit example 4. Recall the example was traditionally 70% of applicants to the MBA program are women. We reviewed 20 applications, and now we want to compute the probability that 17 or fewer applications are from women. From slide 28, we know that N equals 20. A female applicant is a success for this problem since the question is asking about a female applicant. and P is equal to 0.7. So here we are trying to find the probability that X is less than or equal to 17. The sample points 0, 1, 2, 3, 4, all the way up to 17 successes are contained in this event. So in order to compute the probability that X is less than or equal to 17, we can sum the probability of having X equals 0 success plus the probability of having X equals 1 success all the way up to the probability of having X equals 17 successes. Here, the complement's law would make this problem much easier to solve. The complement to the event that X is less than or equal to 17 contains the sample points X equals 18, 19, or 20 successes. Recall, the complement's law says the probability of an event is equal to 1 minus the probability of the complement of the event. So if we have n equals 20 trials or a sample size of 20, we can use this complement's law in order to compute the probability for this case. So the probability of our event is equal to 1 minus the probability of the complement of this event. If we use the binomial tables and look up n equals 20 and p equals 0.7, for x equals 18 successes, for x equals 19 successes, and for x equals 20 successes, we can find their corresponding probabilities. Using our formula, the probability that x is less than or equal to 17 is equal to 1 minus the sum of the probabilities of these sample points contained in the event. If we sum up all of the probabilities in the complement of the event, we get 0.0354. So the probability of the event that we want is equal to 1 minus the probability of this complement, which is 0.9646. So there is a 96.46 chance that 17 or fewer applications are from women. Example 6, hands-on practice. Suppose statistics show that 35% of the students that register for a specific science course withdraw before completing the course. If 18 students register to take this course for this upcoming semester, what is the probability that less than 5 students will withdraw? You should pause the video at this time and go through our basic steps for first identifying that this is a binomial probability experiment, and then use our tables in order to determine the probability that less than 5 students will withdraw from the course. Now that we have finished trying this problem, let's review our answers to see if it's correct. First, we have a sample size of n equals 18 students. There are only 2 possible outcomes for each student. Either they will stay in the course or they will withdraw. Since we are interested in the probability of a student withdrawing, we will name withdraw a success. The probability of a success, or the probability of a student withdrawing, is our p-value, which equals 0.35. We're going to assume that the likelihood of one randomly selected student withdrawing does not affect the likelihood of another randomly selected student deciding to withdraw. Here we are trying to find the probability that less than 5 students withdraw. So we're trying to find the probability that x is less than 5. the sample points x equals 0, x equals 1, x equals 2, x equals 3, and x equals 4 successes are contained in this event. Therefore, we must sum the probabilities of each of those sample points in order to compute the probability that less than 5 students withdraw. If we go to our binomial charts and look for the chart with n equals 18 and p equals 0.35, we can find these probabilities. Here, we list each of the probabilities and sum them together and get 0.1887. So there is an 18.87% chance that less than 5 people will withdraw from this class. With any data set, we are always interested in determining the mean and the variance for the data set. If you know that you have a binomial experiment and a binomial random variable, then it is much easier to compute the mean and the variance for this binomial experiment. If we have a binomial random variable with parameters n and p, then the mean of our random variable is equal to n times p. Our variance will be equal to n times p times 1 minus p. And as always, our standard deviation will equal the square root of the variance. Revisiting example 3, when we flipped the coin 10 times and wanted to know the probability that we get tails exactly 3 times, we can easily determine the expected number of tails in 10 trials. That expected number is equal to n times p. Our n value is 10, and the probability of getting a tails is 0.5. Therefore, the expected number of tails is n times p, or 10 times 0.5, which equals 5. So in 10 flips of the coin, we should expect to get tails exactly 5 times. The variance is equal to n times p times 1 minus p. So the variance for the number of times that we should get tails would be equal to 10 times p equals 0.5 times 1 minus p, which is also 0.5, is equal to 2.5. The standard deviation for the number of times that we should get tails out of 10 flips is equal to the square root of our variance, which is 1.58. Now let's revisit example 4. If 70% of the applicants for the MBA program are women and we review 20 applications, we can determine the expected number of female applicants out of the 20 applications using our expected value formula for a binomial random variable. This formula tells us that the expected number of female applicants is equal to n times p. In this case, our n equals 20 and our p equals 0.7. Multiplying those values, we get 14. We should expect that 14 out of 20 of our applications would be from females. The variance for the number of female applicants that we should expect to see is equal to n times p times 1 minus p. For our problem, n equals 20, p equals 0.7, and 1 minus 0.7 is equal to 0.3. Therefore, our n times p times 1 minus p gives us a variance of 4.2. The standard deviation is the square root of the variance, which equals 2.05.